So we're starting on section 5.4, and we're going to explore the relationship between differentiation and integration. And we're going to start with theorem 4. It's a very important theorem. It says if f is continuous, on AB, then capital F of x equals the integral from a to x f of t dt is continuous on AB and differentiable on the open AB. And it's and its derivative, not the anti. Is f of x. So capital F prime of x is d dx of the integral from a to x f of t dt. That equals little f of x. This is the fundamental theorem of calculus. Fundamental theorem of calculus. Oops.
That's the capital F.
Remember we talked about that. That's the original function. We did that at the very beginning. Capital F is the original function. Little f is the derivative.
So little f is 0 and capital F.
Okay, I see what, yeah, if you think about that, yes. But this is the derivative. And this capital F is the antiderivative or the original function. Part 1. Now, what we're trying to get at is if you look at the derivative and the integration, they're opposite operations, so they cancel each other out. But then we have to plug in plug in this expression right here, whatever's at the top. Okay. Now we're going to work some problems, and then we're going to do the second part of the fundamental theorem calculus. Because that is the theorem. Somebody wrote that and said and proved it.
So obvious.
Exactly, but everything has to be proven. Mathematics, we have to prove it. All right, so let's do an example and see what they're talking about. Right. And it's going to lead us to what we did yesterday as well. Okay, so it says use the fundamental theorem of calculus. To find dy dx if a. We've got y equals the integral from a to x, bless you, of t cubed plus 1 dt. So what we want to do is we're given that y is that integral, and we want to find the derivative of that. So we're going to do dy dx on both sides. So d dx of the integral a to x t cubed plus 1 dt. Now, this is going to be the derivative of y. So dy dx, what we're going to do is these two pieces basically cancel each other out, and we have to plug this x into the t because they're opposite operations. You take the derivative of the integral, they cancel each other out. Well, it's the derivative of the antiderivative gives you back what you started with. So whatever you had. It's like adding 2 and subtracting 2. It's not changing the problem. The antiderivative is the original, but we're looking for the derivative of the original, where the original was an integration instead of a regular function. So what it does is it gives us back what we have, except we're putting in that x. So it's going to be x cubed plus 1. But then we have to multiply that by the derivative of what we're plugging in. So dy dx equals x cubed plus 1 times 1. So dy dx equals x cubed plus 1.
Where does it say we have to multiply by the derivative?
Because when you take the derivative, I don't know where it says that, but that's what you do,
Chain rule.
chain rule. But it's what we're plugging in, not what's there. We're not differentiating what's there. Notice what I have right here. What I have right here is what I have right here, except I plugged in the x. Now we can do it the long way. Let's do the long way. We want to find the derivative of this thing. So if we start off with y equals the integral of 8x t cubed plus 1 dt, we would first find the integral, the integration. We first would do the integration. So this would be y, well, capital Y, equals t to the 3 plus 1 over 4 plus t. And then since we have, this is a definite integral, we would do a to x, right? So that would be t to the 4th, or excuse me, we'll do one, however you want to do it. Let's just leave it like that, t to the 4th. T to the 4th over 4 plus t from x to a. So we do upper minus lower. So it would be x to the 4th over 4 plus x. Yeah, it's from a to x. But we do upper minus lower, so x is first. Right. You say it from bottom to top, but you work it from top to bottom. Minus a to the 4th over 4 plus a. Okay, so that would be my function. I can't do anything with it, but that's my function. That's my original function. Now I'm going to take the derivative of my original function. So I want to do d dx of my original function is d dx of x to the 4th over 4 plus x minus a to the 4th over 4 plus a. Okay, so this would be 4 times x cubed over 4 plus 1 minus, now, we're taking the derivative with respect to x, so we hold a, and there's no x, so that would go to 0. We hold a, there's no x, that goes to 0. It's like it's a constant. It's just saving doing the extra work. Yeah. Well, sort of. We're changing the t to something else. Because right now we're putting in an x. Let's look at the next one. You'll see what I'm talking about. So I could work it out the long way by doing the integration and then doing the differentiation. Yes, sir. Because we're taking the derivative with respect to x. So a is like a constant because it's not x. Remember, like if we did dy, when we had xy, we held the y and took the derivative with respect to x and then did the back and forth. So a is like a constant. We're treating a as a constant. And so when you take the derivative of a constant, it's 0.
A is not.
A is not a function. It's a number. Okay? Because remember, it's a to b. A is a number in our interval. All right, let's look at the second one. We're going to do y equals the integral from 1 to x squared of cosine t dt. Okay, so now we're going to take the derivative of both sides. So dy dx equals d dx, the integral from 1 to x squared, cosine t dt. Okay. So notice the bottom is the number. The top is the expression. So we're going to do cosine of x squared times the derivative of what we plugged in. So that's cosine x squared times 2x, which we'll write as 2x cosine x squared. Left my x off.
Is that DT telling you you're gonna?
Yeah, because we're going to get into something later on that explains that more when we have use substitution. But we have to have, in order for it to work, we have to have the derivative of what we're plugging in. Okay. Because these two things are canceling each other out. So we're left with what we had. It's like doing x plus 2 minus 2. These two cancel each other out, and we're left with what we had, which is the x. We don't worry about it because it's going to be a constant. It's going to be a number. So if I did it the long way, if I did it like I did over here, come on. If I did it like I did on this side, that back end is going to be a number. And when I take the derivative of a number, it goes to 0. So if we did it the long way, nope. Well, nope. like if I'm going to do this one. So what gave me cosine? Oh, that's supposed to be t. What gave me cosine? Come on, people. What's it? So there you go. Sine t. No, if I went from sine back, it would be negative. Because cosine is negative sine. Yeah, we got to do the anti. So this is from 1 to x squared. So this would be sine x squared minus sine of 1. And then now I got to do dy dx, d dx of sine x squared minus sine of 1. Okay, so the derivative of sine is cosine x squared, but I got to do the chain rule, which is 2x, minus sine of 1 is a number, which would be 0. So I'm just trying to cut out that middle step of integrating and then differentiating. They cancel each other out, and I just plug in that number and do the, and so you see I have to have the derivative of what I'm plugging in because that's the chain rule. It's what's inside.
So if you take the derivative, sine x squared, change from x.
Nope, it would still be, when you do the derivative of sine x squared, and then you do the derivative of x squared, which is where the 2x comes from. You do the chain rule. You do the outside sine, and then you do the inside x squared. Because then you have x and t. And you're not, that's where we get the 2x from. We're doing the dt part, the derivative with respect to what we plugged in. Because we started off with y and t and we plugged in x. We replaced t with x. We still have 2 letters, y and x now. We don't have a t because we plugged in for it. That's what the theorem says. It's from a, which is a number, to x, f of t. We plugged in the f of t, which gives us the, or we plugged in the x for the t, which gives us f of x. Because we said that f is continuous on AB, then f of x, capital F of x equals the integral, which means f of x, capital F of x, is the antiderivative of f of t. F of x is the original, so it has to be same units. X and t, we got to convert to x's. And it says, and its derivative f of x. So we're just trying to show you that what you started off with when you started off with the original function and did the derivative, and you got that new function, it's the derivative of the integration. It's the same thing. You're overthinking it. Let's try another one. All right, see. You got y equals the integral from 1 plus 3x squared to 4 of 1 over 2 plus e to the t dt. Now, remember, it's a to x, number to expression. So we need to fix this. And remember, we learned yesterday, if we want to flip-flop the two little numbers, we put a minus in front. And so now I can flip-flop the two numbers. And then that's 1/2 plus e to the t dt. Okay, so that equals negative 1 over, oh, I skipped a step. dy dx equals d negative d dx integral 4(1) plus 3x squared 1/2 plus e to the t dt. So that gives me negative 1/2 plus e to the 1 plus 3x squared times the derivative of what we're plugging in. So that's negative 1/2 plus e to the 1 plus 3x squared times 6x. That's 2 times 3 is 6. And just to clean it up a little bit, negative 6x over 2 plus e to the 1 plus 3x squared.
What does the 4 tell us?
That was the number. We start at 4. So if we plugged in the 4, we would get a constant, and that would differentiate out to 0. So we don't use it. It's just the lower limit.
So we're not,
Not here. We're not. And if you're doing the fundamental theorem of calculus part 1,
I don't agree. You can give us the different.
because you have to have a starting and an ending point. You can't just have an ending point. Like, exactly, it's a placeholder.
And how would we know?
If you have a letter in the upper, you have a variable in the upper. Notice the ones we worked yesterday were 2 to 3, negative 2 to 4. They were two numbers. Okay, here, the ones we work in is a number to something, an expression, something with a letter. Yes. We're heading that way. All right, so y'all ready for the second part of the theorem? All right, second part of the theorem. Theorem 4 continued. Yes, I'm recording. I had a panic attack there for a minute. I didn't think I was recording. That's okay. Theorem 4 continued. The fundamental theorem of calculus part 2. You don't start with the first T. Fundamental theorem of calculus part 2. It says if little f is continuous over AB, yeah, little f, and little f, no, big F, is the antiderivative of little f on AB, then the integral from A to B of little f of x dx equals capital F of B minus capital F of A. And if you remember, that's how we calculate definite integrals. That's what we did yesterday. So be prepared, I haven't decided yet, but be prepared to write both parts of the fundamental theorem of calculus as a test question.
Just the formulas.
Just the whole thing, words and all. Words and all. That's the big F, the original function. The antiderivative is the original function.
So F is
The capital F is original. The antiderivative is your original function.
So basically, that's just saying you don't have to find the anti.
Yeah, you do have to find it, but if, instead of having to draw all those pictures and coming up with all those little sums, this is a way of avoiding all those, that summation of all those little rectangles, which is what we really are supposed to be doing to find the area under the curve. So we're going to do it, we're going to use this. So just like limits was the basis for derivatives. Okay, the area under the curve, it shouldn't have been in that section though. The area under the curve is the basis for the integration. Well, we're in theorem 4, section 5.4 instead of 5.3. At the bottom, the lower limit, yeah, it's a placeholder. Now it's not, because notice the difference in what we're doing now. Now we have A and B. A, B, B. So those are numbers. So we're going to actually do the work. Whereas on the ones above, it was a placeholder. Usually the left-hand side of our, if you noticed, it was the left-hand side of our interval. That's the A. See this A? The area under the curve is what we're solving, we're doing the integration. That's what we're doing. The whole idea is getting the area under the curve. But we're trying to avoid having to draw the picture and do the little rectangles. I don't understand what you mean by one line. Uh-huh. One graph, is that what you're talking about? Okay, yes. Well, there's one graph, but we're going to get into the situation where there are two graphs. Right now, there's one graph, and we're referencing off the x-axis. Yes, I didn't understand what you meant by line. Okay, so this gives us a way to evaluate a definite integral without having to calculate the limits of the sum. I just said that. So let's look at an example. We want to solve. And this is the integral from 1 to 3 x cubed dx. Now, notice how this is the integral. We're not looking for the derivative. We're looking for the antiderivative. So we go x to the 3 plus 1 over 3 plus 1 is 4. And we're going from 1 to 3. Okay. So that's going to be, that's x to the 4th, right? So we're going to do 3 to the 4th over 4 minus 1 to the 4th over 4. Okay. 3 to the 4th is 81 over 4 minus 1 over 4, which is 80 over 4, which is 20. Yeah, so it's just that's what we did last time. So we're not really doing anything new here. The new stuff was the ones where we had the letter, the expression. All these are gonna be the same. Yes, we do that. Okay, then you still add one. So if it's a fraction, say it was x to the 3/4, then you would do 3/4 plus one, which would be 7/4. And then 7/4 underneath. And then 4/7 x to the 7/4 and plug in. Still the same. Oh, I did too fast. If it was an integral of x to the 3/4 dx, and say it was from 1 to 3. We shouldn't have anything like that yet. We haven't got the reverse of that. The antiderivative of it. Because we would pull the 3 out. We would have 1 over x plus 1 dx. And so it might be an LN situation, but we haven't done anything with the sum in the bottom yet. Because if you got 1 over x, that's that's ln of absolute value of x. So it might be ln of absolute value of x plus 1. All right. So from 0, in that eraser, 0 to pi over 4, can't read my handwriting today. And it's secant squared x dx. So we're going to integrate that. What does secant squared go back to? Tangent. We're seeking a tan. So tangent x from 0 to pi over 4. Yeah. No. Reverse. Look at the derivative and go back. You see. So it's on the front page, I think. Over on the side. I don't know. All right, so to evaluate these, you need to make sure you have your calculator in the right mode. So if we're doing tangent of pi over 4 is radians. Or you can say pi over 4 is 45 degrees, if you know your degrees. So tangent of pi over 4 minus tangent of 0. Pi over 4 is 1. Tangent of pi over 4 is 1. Tangent of 0 is 0. So the answer is. Now, we're not going to ever get away from the area thing. Sorry. Pi over 2 is halfway, so pi over 4 is a quarter. That's the definition.
Square root of 2 over 2.
Square root of 2. Sine over cosine. All right. Example. Yes. That would be the area under the curve. Find the area of the region bounded by the graph of y equals 2x squared minus 3x plus 2, the x-axis, and the vertical lines. Oh, I can't spell today. I can't spell any day. Well, I have a little dyslexia, so. And I have a habit of saying things, and as I'm saying, trying to write something else.
Is that ampersand before the?
This is just an and. And. Okay, so let's draw that picture. X, Y. And we're going to do 0, 1, and 2. When we plug in 0, we get 2. When we plug in 1, we get 2 minus 3, 4 minus 3, which is 1. When we plug in 2, that's 8 minus 6 is 2 plus 2 is 4. One, two, 1, 2, 3, 4. At 0, we get 2. At 1, we get 1. At 2, we get 4. And so we want this area. You see my little rectangle there that I'm moving around. We want that area. Now, it's not as easy as the ones we did yesterday, because yesterday were straight lines, really straight lines, or they were a definite curve like the semicircle. So we knew formulas for those. This one, if we were to do it like we learned before, we would do the little rectangles and keep breaking it up in little rectangles and trying to calculate it. But we're not going to do it that way. We're going to do it the way we learned by integration. Okay, so no, but just to give us an idea of what we're looking at. So we're integrating. What's my lower limit on my picture? What's my upper limit? 2. We're integrating the 2x squared minus 3x plus 2x. Okay. Because I can have my original formula can be a derivative, and I have another one that it came from. Every formula has a previous one. Well, we're just looking for the area under the curve for this particular problem. Yeah, usually they do it like y prime or y double prime or something like that. But we can still, whatever we're looking at, there's some function that is an antiderivative of the one we're looking at. Right, so this is, we're doing the integration of this one, so our original will be the other one. This is what they gave us. Okay, you're getting hung up on words. They're giving us this function. We're going to integrate this function and plug in the 0 and the 2. Antiderivative, this function. Yeah. It makes people cry. Well, that's one of the reasons why I tell everybody sometimes it's just better to learn the how now, and the why comes as we get into other things. So, you know, we learned why we were integrating because we're doing area under the curve. It just kind of feeds. All right, so we're going to do the antiderivative. So 2 times x to the 2 plus 1, which is 3, minus 3 times x to the 1 plus 1, which is 2, plus 2x from 0 to 2. And for those of you who weren't here last time, we don't do the plus c because we've got those bounding numbers, the 0 and the 2. If it was an integral without any numbers on it, that's when we put the plus c. But because we've got that 0 and that 2, we don't have to put the plus c. All right, so this is 2/3 x cubed minus 3/2 x squared plus 2x. And we're going from 0 to 2. We're going from 0 to 2, or excuse me, from your side, 0 to 2. We start with the upper bound, 2/3 times 2 cubed minus 3/2 times 2 squared plus 2 times 2 minus I know I don't have to put it, 2/3 times 0 cubed minus 3/2 times 0 squared plus 2 times 0, which this whole thing goes to 0. Why do I do the? Why, no, I didn't hear the question. You always do your upper bound minus your lower bound. It's the formula. Yep. See, look, Noah, it's f of b minus f of a. So the upper bound minus the lower bound. That's the formula. No, it's just, we read from smallest to largest, we're hoping it'll make it always positive. Because if you do your largest number minus your smallest number, you should get a positive, but it doesn't always work that way. What if we're underneath? Okay, so this gives me, let's see, 2 cubed is 8 times 2 is 16 thirds minus, one of those twos cancel and we get 6 plus 4, which is 10 thirds square units. And that is the area of the shaded region, the yellow part.
It's not even.
Mm. Depends on how big you draw it. Oh, 10. It's 3 1/3 square units. Okay. Now, when your function is in multiple sections, follow this procedure. One, subdivide AB at the zeros, or your x-intercepts.
So
Intercepts of f to integrate over each subinterval add absolute value of the integrals. So what they're talking about is something like or, oops, too far. So you've got area 1 and area 2. Area 1 and area 2. Go away. You go away. Thank you. All right, so we're going to look at a picture that has, or a problem that has that kind of situation. Okay. So example. Find the total area of a region bounded between the x-axis and the graph of y equals x cubed minus 6x squared plus 8x on 0, 4. Okay. So first of all, let's draw our picture. X, Y, 0, 1, 2, 3, 4. Plug in 0, we get 0. Plug in 1, we get 3. Plug in 2, we get 0. Plug in 3, we get -3. Plug in 4, we get 0. Okay. 1, 2, 3, 4. At 0, we get 0. At 1, we get 3. At 2, we get 4. No, 1, we get 3. 2, we get 0. At 3, we get -3. 1, 2, 3, 4. And at 4, we get 0. Area 1, area 2. Okay. So the first thing we have to do is decide what are our subintervals. So we know we're going to start at 0 because that's my lower limit. Where is the next x-intercept? 2. So from 0 to 2, we're going to integrate x cubed minus 6x squared plus 8x dx. Plus, then we're going to start at 2, bless you, and go to the next x-intercept in case there's more than one inside of the interval. Okay, so we would just keep doing this until we reach the end. In this case, we reach the end at 4. X cubed minus 6x squared plus 8x dx. If we got numbers, then we're not going to do work with that. Okay, so we're going to integrate. So that's x to the 3 plus 1 over 4 minus 6 times x to the 2 plus 1 over 3 plus 8 to the x to the 1 plus 1 over 2 from 0 to 2. And then we're going to have the same thing, x to the 4th over 4 minus 6 times x to the 3rd over 3 plus 8 times x to the 2nd over 2 from 2 to 4. Okay, so let's clean that up a little bit. That's x to the 4th over 4 minus 3 goes into 6 2 times, so that's 2x cubed. 2 goes into 8 4 times, so that's 4x squared from 0 to 2. X to the 4th over 4 minus 2x to the 3rd plus 4x squared from 2 to 4. Okay. And so now we just plug in the numbers. Do I really need to plug in 0? No, because it's all going to cancel out. So 2 to the 4th over 4 minus 2 times 2 cubed plus 4 times 2 squared. All right. Oops, I forgot my plus sign. Plus 4 to the 4th over 4 minus 2 times 4 cubed plus 4 times 4 squared minus 2 to the 4th over 2. I'm going to run out of space over 4.
Well, you're already doing that. You don't have to.
Because it's got to do absolute values. You have to separate them.
You're gonna get.
Right. Right. So you're saying I'm calculating it twice. Yes.
Know the answer.
Right. But I'm going to go ahead and finish writing it out. Minus 2 times 2 cubed plus 4 times 2 squared. All right, so this comes out to be 4 minus, well, 4, because I already took the minus 0 off. Plus, and this comes out to be 0 minus 4. But I have to do the absolute value of those areas. And so I get 8.
And then the negative.
Because those are directions.
Negatives come from minus.
Yeah.
And then that's why you have to pass.
Because see, it's area above and area below. So if I use the area above and the area below as is, there would be no area. 4 minus 4 would be 0, but there's area. So it's just saying that there's area above and area below. And so we do the absolute value to get that area plus that area together. All right, we're going to do one more problem because we got the alpha theta coming in a few minutes. If y'all want to stick around, you can. So example, yeah. Find the area of the shaded region. Okay. So one, two, three, 4. Pi over 6, pi over 3, pi over 2. There's no undo button, dang it. Oh, there, thank you. Okay, so our equations that they have not given us is y equals 4. That's our upper. And y equals 3 cosine x plus 1. No, they will have labeled on the picture. So what we're going to do is to construct integrand upper function minus lower function. Because what we're doing is we're taking the y equals x, everything below that, which would be a rectangle, that would be 4 by pi over 2. And we're removing what is underneath the cosine, 3 cosine x plus 1. So it's upper function minus lower function. So,
So that 3 cosine x plus 1 is,
no, that is just the derivative of the curve. I mean, not the derivative, that is the equation for the curve. No, it's just the equation of this curve right here.
so we haven't commented.
We haven't done anything yet, no. This is just y equals 3x, 3 cosine x plus 1 is just that curve. And then this is y equals 4. That's the other one. What? No, they don't have to be separated equally. It's just where you hit the x-intercepts. Now, in this case, we're going to do, there's no x-intercepts. So we're going to go from 0 to pi over 2. But what we're going to have to do is take the upper equation, which is 4, and subtract out the lower equation, which is 3 cosine x plus 1 dx. So we get from 0 to pi over 2, 4 minus 3 cosine x minus 1 dx. Huh?
Why do you need to?
Because it's the stop, it's the bounding on the top of it.
Just do 4 times 5 or 10.
That would be the whole big box.
Yes.
Then we would have to take out the area of this. It's the same thing. Yeah, it's just, we're doing it would be 4 times x, which is what you're talking about. When we integrate it, we get 4 times 5. Y'all getting ahead of me. All right, so then that would be using, right now we're using rectangles. But instead of doing that, instead of calculating all those little rectangles, we're doing the integration, which is the same thing. Somebody somewhere calculated all those little rectangles a long time ago. All right, now notice what I did. I combined the 4 and the 1 because, why integrate 3 pieces when I can integrate just 2? So this is going to be 3x minus 3 times what? Sine x from 0 to pi over 2. So that's 3 times pi over 2 minus 3 times sine of pi over 2 minus 3 times 0 minus 3 times sine of 0. Okay. So that gives me 3 pi over 2. What is sine of pi over 2? 3 times 1 minus 0 minus, what's sine of 0? 0, because it starts in the corner. So that's 3 pi over 2 minus 3. And that is your answer. Square units. Now, I still have 1, 2, 3, 4 more examples, but I'll make a video and post it of those 4 examples because we're supposed to only cover this in one day. All right? Okay. Stop sharing.
So what does it look like when you